Hello and welcome. In this lesson, we're going to learn about arrays, which happens to be one of the most fundamental tools in programming. We'll look at the different types of arrays, including static and dynamic arrays. We'll learn how to access, modify, and manipulate elements within an array. We'll also learn about referential arrays, how they store references in memory, and why they are important. By the end of this lesson, you will know how to perform basic operations on arrays, look through their elements, and most importantly, apply them to solve real-world problems. So let's get started. What is an array? An array is a data structure that allows us to store multiple values in a specific order. Think of it as a row of labeled boxes, where each box holds a value and has its own unique position called an index. With this index, you can quickly locate any value from the array. Now keep in mind that arrays have a fixed size. All the items must be the same type. This means that when you create an array, you need to decide two things up front: how many values it will hold and what type of data it will store. When an array is created, the computer allocates a block of memory where all the elements are stored side by side in contiguous locations, just like boxes lined up in a row. The starting point of this block is called the base address. This is the memory address of the first element in the array, and it serves as a reference point for accessing any other element. Each box has a number on it, and the number is called the index. In most programming languages, indexing starts at 0. So the first element has the index of 0, the second element has 1, the third has the index of 2, and so on. So let's say you are storing the ages of students in an array, and each age takes up about 4 bytes of memory. Now let's say the base address of the array is 1000, and you want to find the age of the students at the index 3. This is how the computer computes this. It uses the formula memory address is equal to base address plus index multiplied by the size of each element, which is 1000 plus 3 times 4, which is 1012. This means that the student's age is stored at the memory address 1012. However, you don't need to worry about memory addresses, as these are handled internally by programming languages. You can simply make use of index. Back to arrays. Because every element in an array has a fixed size, this calculation is fast and efficient, allowing computers to quickly locate any value in memory. But this comes with a problem. What if you suddenly need to store more values than you originally planned? Since arrays are located in a continuous block of memory, you can't just add extra elements beyond the initial size. Also, if the array becomes full and you need more space, the only option is to create a brand new array with a larger size, copy all the existing values over, and then add the new ones. This, of course, takes time and memory. This is where dynamic arrays comes in handy. Unlike static arrays, which have a fixed size, dynamic arrays can grow or shrink as needed. Instead of being strictly limited by its initial size, a dynamic array starts with a certain capacity and expands automatically when it reaches its limit. How does it do this? It creates a larger memory block, copying the existing elements and then storing the new values. However, this comes at a cost as well, but in return, it offers the flexibility that static arrays don't have. In Python, lists are implemented as dynamic arrays, meaning they adjust their size automatically as elements are added or removed. This way, you don't have to define a fixed size in advance. Also, Python lists can hold values of different types, which leads us to the concept of referential arrays. Unlike in standard arrays, referential arrays store memory addresses or pointers that reference data stored somewhere else. This is different from standard arrays, which store actual values like integers, floats, or characters. The key thing to remember about referential arrays is that they still have a fixed type, but instead of holding the data itself, they hold references to the data. Let's say we want to represent patient detail using arrays. Normally, each patient has a record containing details like name, age, and medical history. The problem here is that these details are of different data types, meaning they take up different amounts of space in memory. For example, a patient's age is an integer and may take up about 4 bytes of space. The name, which is a string, could take several bytes depending on how long it is. The medical history, which is a bit lengthy, may take hundreds or even thousands of bytes. If we try to put all this data into a single array, it won't work. The reason is that arrays normally require each element to be the same size. A better solution is a referential array, which stores pointers or memory addresses instead of actual data. Each pointer takes up a fixed amount of space, keeping the array structured and efficient while allowing quick access to patient record stored elsewhere. This is why Python lists can hold items of different types, including integers, strings, and so on, all in one list. For example, if we create a list like this, we'll call this patient and assign it to a list. And in this list, we're going to have the patient name. So for the name, we can call it Johnson. Then we have the age. We can give it 25. And we can put the medical history. For this medical history, we can call it shortness of breath. So this is our list. Python doesn't create one big memory block to fit all these 3 elements. Instead, it makes an internal array of references where each reference points to the actual value stored somewhere else. This makes Python list flexible and dynamic. This way, list can store multiple data types and grow in size efficiently. This brings us to the concept of shallow and big copies. Since Python lists are referential arrays, making a copy of a list doesn't produce an entirely new list, because if you update an element inside the copied list, it can also affect the original list. Why? Because both lists are pointing at the same data. This is what we call shallow copy. It makes a new list, but instead of copying the actual data, it just copies references to the original data. Anytime you slice a list or use the list function or call the copy method from the copy module, you are making a shallow copy. Now, this is the tricky part. Shallow copies are usually fine when you're working with simple immutable types like numbers or strings. But if you have a list with mutable objects like nested lists, you may get an unexpected outcome. Let's take a look at this list, and we're going to call it original. So I will have a variable original, and I'm going to assign it to a value. So for the value, I'm going to have some numbers. So we'll have 1, 2, 3, and 4. I'm going to create a copy of this list. So I can call it copy 1. And for the copy 1, I'm going to be making use of slicing. So I can have original, then I'll use my slicing operator, use a colon, and then I'll close the bracket. So this is going to give me a copy of the original. I'm also going to make another copy of the original, and this one is going to be copy 2. So this is copy 2, and I'm going to be making use of the list function to create this copy. So I'll have list, and I'll have original. I'll close the parenthesis. Now, let me go ahead and make changes on the original. And I'm going to be targeting the first element in the original. So I'll have original. I'm targeting the first element, which is 0. And I will assign it a different value, which is 99. So let's go ahead and print our lists. So this one is print original. I'm also going to print the copies. So this is print copy 1. We'll have print copy 2. And we'll run the program. And you can see that only the original was affected by the update. The rest remained intact. In as much as we performed a shallow copy, the changes only affected the original and it didn't affect the copies. And the reason for this is that we're working with immutable types. We're dealing with numbers. So let's take a look at another example. And in this example, I'm going to be using nested lists. So I'll go ahead and use original is equal to, I'm going to have an outer list, and this list is going to contain 2 other inner lists. For this one, I'm going to write 1 and 2. I'll close it, put a comma. Then the next one is going to be 3 and 4. So this is a nested list. And I'll make a copy of this list, but I'm going to be using the slicing. So have copy 1 is equal to original. And I'll use colon, close the square bracket, and I'll go ahead and make changes on the original. So I'll have original, and I'm going to be targeting the first element in the first list. So I'm going to use 0 here, and I'm also going to use another 0 here. So this is targeting this particular element, and I'm going to assign it to a value. So this value, let's call it 99. Now let's go ahead and print our original list and our copy. So this is print original, and we'll have print copy 1. So let's go ahead and run the program, and you can see that the changes I made on the original also affected the copy, and this is because we performed a shallow copy. So if you don't want this type of thing to happen, then you have to perform a deep copy. A deep copy doesn't just copy references, it creates entirely new objects in memory. This way, changes made in the copied list don't affect the original. And for us to perform the deep copy, we're going to be importing the copy module. So I'll start by importing copy. Then I can go ahead and copy this list and paste it here. I'm going to create a copy of this list, but I'm going to be using the deep copy to do so. So I have copy 1 is equal to copy dot deep copy, and I'm going to be putting in original here. So I've made a copy. This one is a deep copy. Now let me target the first element within the nested list and give it a new value. So I will have original 0 and 0, and then assign it to 99. So let's go ahead and print original and the copy. So print original, print copy 1. Then we'll run the program, and from the output you can see that the changes only affected the original without affecting the copy, and this is because we performed a deep copy. With this deep copy, the original and copy 1 are 2 independent entities. So if you need to preserve the original data while making independent modification, deep copying is the best way to go. Now we'll look at the operations we can perform on arrays, like accessing the elements or indexing, traversal, insertion, deletion, searching, and sorting. And from now on, we'll be treating arrays as lists. We'll start with accessing elements in arrays. Accessing an element in an array means retrieving the value stored at a specific position. Let's take a look at this array To access an element, all you need to do is to specify the index. For example, if we want the third element, we'll simply specify the index for the third element, which is 2. So let's try this out using Python. We'll start by defining our array or list. So this is array is equal to 10, 20, 30, 40, and 50. So if you want to access any element within this array, all you have to do is to indicate the index of the item that you want to access. Of course, lists are 0 index based, which means that the first element has the index of 0. This one has the index of 1, 2, 3, and 4. So if you want to access the first element, you're going to be providing the index of 0. So let's go ahead and try this out. So we can have print and we'll specify the index. So this is going to fetch the first element in the array. And if we want to fetch the third element, we're going to use print. We'll specify the name of the array or the list. Then we'll put the index. For the third element is going to be 2. Then we'll close our parenthesis. Then we'll run it. You can see the output is 10 and 30. This operation runs in a constant time, meaning it has a big O of 1 regardless of the array size. Now let's look at traversal. Traversal involves going through the elements in an array one by one. You may want to print, modify, or perform calculations on them. So we're going to be working with our original list. So we have array is equal to, we'll have 10, 20, 30, 40, and 50. To traverse this array, we'll simply perform a loop on it. We can use the while loop, we can use the for loop. But let's use the for loop. So to do this, you simply write the for keyword. Then we can put nums here in array. Then we'll go ahead and print nums. Or better still, we can have this as num. Then this is going to be num. Then I'll run it. And this is going to display all the elements within the array. When we traverse an entire array, we are essentially processing each element one by one. This means that if there are n elements in the array, our loop is going to execute n times. Therefore, the overall number of operations increases linearly with the size of the array. Hence, we can say it has a big O of n. Let's look at insertion. Insertion involves adding a new element at a specific location within a list. You can insert an element anywhere, but it is most efficient to do so at the end. Normally in standard arrays, if you insert an element at any position other than the end, all the elements that come after the insertion point must shift to the right to make room for the new element. In Python, you can add an element at the end using the append method. Since append doesn't require shifting any existing element, it operates in a time complexity of big O of 1, which is the best case scenario. So let's see how it works. In Python, you can add elements at the end using the append method. So I'm going to quickly copy this list and put it here. So if we want to insert at the end, that means after 50, we're going to be using the append method. So we can write array.append, then we'll provide the value that we want to insert. So let's put it as 60. And let's go ahead and print our array. Print array. And this is going to insert the element at the end. This is considered to be the best case scenario because when you insert at the end, there is no shifting of elements. And the time complexity for this is the big O of 1, is a constant time operation. However, When you insert an element anywhere other than the end of the list, you can use the insert method to specify the index. The worst case scenario is inserting at the beginning of the list. In this case, every existing element has to shift one position to the right, and this has a time complexity of the big O of n. So let's go ahead and demonstrate this insertion. So I'm going to edit this, and for the insertion, you provide the array, then you use dot insert, then you specify the location where you want the insertion to be done. If you want to insert at the beginning, that means the index will be 0. Then you can provide the value that you want to insert. So let's insert 5, and we go ahead and print the array. We'll run the program, and you can see that the insertion was done at the beginning. So if you want to insert any other position, you simply indicate the position. If you want to insert at the 3rd position, you can simply put 2 for the position, and this is going to insert it at the 3rd position. Next, we'll look at deletion. Deletion involves removing an element at a specific location within a list. You can delete an element anywhere, but it is most efficient to do so at the end. Normally in standard arrays, if you delete an element at any position other than the end, all the elements that come after the deletion point must shift to the left to fill the gap left by the removed element. You can remove an element from the end using the pop method without specifying an index. And since this operation doesn't require shifting any existing element, the time complexity is a big O of 1, which is the best case scenario. So let's see how to do it in Python. We're still using this same array, and we're going to be using the pop method to remove the last item, which is 50. And for this operation, we'll simply write array.pop without specifying the index. So let's go ahead and print our array. This is going to remove the last element. So we now have 10, 20, 30, and 40, no more 50. This is a constant time operation because we're removing from the end. So if you want to remove from any other position, you can use the pop method specifying the index where you want to perform a deletion. You can as well use the remove method. So let's go ahead and try out the pop method with index and the remove method. So far we're left with 10, 20, 30, and 40. And we're going to be using the pop with an index to remove an element in a specific position. We'll have array.pop, and we want to remove the second element. The second element has the index of 1, so this is going to be 20. So I'll simply close this, and we'll print the array. So you can see 20 has been removed. Another way of removing is by using the remove method, but the remove method removes the first occurrence of a given value. So far we're left with 10, 30, and 40. Let's say we want to remove 30. We can write array.remove, and we'll specify the value that we want to remove. And in this case, we're going to write 30, and we'll print the array. So 30 has been removed. So whenever you remove an element at any position other than the end, all the elements after it must shift to fill that gap, resulting in time complexity of the big O of n. So far, we've looked at how we can access elements in an array, how we can perform insertion, deletion, and traversal. Apart from these basic operations, you can also search through arrays or sort their elements, but we'll look into this when we get to searching and sorting algorithms. Apart from lists, Python has other built-in linear collections like tuples, strings, and ranges. These collections share almost the same characteristics. They store their elements in a specific order and allow you to access those elements by their index. For example, you can access individual elements by their index. You can use slicing to grab a portion of the data, and you can loop through them using a for loop.